Hello, everyone. All right, so we didn't get to finish all of the examples in the 3.5 and 3.6 notes in class. So I wanted to kind of run through some of these last couple examples that we didn't get to. Okay, so in section 3.5, which is our higher derivatives, we were able to do most of these guys. The only one we didn't get to was this last one here. Okay, so it says that this graph that we're given represents acceleration of an object in motion. And we want to know when the object is slowing down. Okay, so let me come back up here and I will put our table in here. So if our original is increasing, that means my derivative is above the x-axis. If my original is decreasing, then my f prime, my derivative is below the x-axis. And if I'm at a max or min, right, if I'm at a turning point here, that means I have an x-intercept on my derivative. Okay, so we're going to use these ideas down here. This is the acceleration of an object. That's what this graph gives me. And I'm asked, when is the object slowing down? Okay, so if something is slowing down, what does that mean? If you're slowing down, that means that the speed that you're going at goes down over time, right? That's what slowing down means. Your speed is going down. So that means your speed is decreasing because it's going down. Okay, so I want to know when the object's speed is decreasing. But I don't have, this isn't a graph of speed, right? This is not velocity. This is acceleration. So in order to answer this question, I have to figure out what the connection between speed or velocity, right? Because speed is just velocity, but without the direction with it. And acceleration, what's the connection between speed or velocity and acceleration? Yeah, acceleration is the derivative of speed. So if the speed is decreasing, then what's happening on the acceleration graph there? Well, again, acceleration is the derivative of speed or velocity. So that means that velocity or speed is going to be my original here, and acceleration will be the derivative of that. So again, if my speed or my velocity is decreasing, that means my derivative, my acceleration, is going to be below the x-axis. So really, this question is asking us, where is my acceleration below the x-axis? Well, it's right here, right? And so where does that happen? Well, it happens between time 0 and time 2. And I'm going to say when it was slowing down, I'll just say everything between 0 and 2. That's how I'll represent this, because this represents every single number between 0 and 2. I'm not going to include 0 and 2 themselves, just because at those points, um, the um, we aren't really truly below the x-axis anymore. So at those points, our speed isn't increasing or decreasing. It's just kind of leveling out. Those are the places where our speed kind of changes from increasing to decreasing. And so we aren't truly decreasing there, so I'm not going to include those. So you could give it to me in, I didn't say, give me an interval notation, so you can do it that way. You can say between um, time 0 and time 2, or however you want to say that. I'm not going to be super picky about how you write it. I think when Achieve gives you questions like this, it's going to want your answer in interval notation, and it'll tell you that. But the hard thing about this is connecting what you have in the graph to what you're asked about. And again, do that with derivatives and use this table to help you. Okay, so that was the last one in 3.5. And then there were a couple in 3.6. So in one of my classes, we were able to get through all of these notes, but we didn't do much on the in-class activity. And in my other class, we did one of the problems on the in-class activity, but we didn't finish the notes. So I'm going to kind of do both, and you can pick and choose what you need. So I'm just going to fill these in real quick in case you need them, and we can come back and refer to those. And cotangent is negative cosecant squared of x. Okay. All right. So in 3.6, we got our derivative of trig functions, and we figured out how to do this. I think these two are easiest to get graphically from our back pocket functions and knowing how slope graphs connect. The rest of these, once you know your sine and cosine derivatives, the rest of these you'll use by writing each of these as trig identities, come back to sine and cosine, and then do quotient rules, and that's how you'll end up with those. Okay, so we were able to do this one in both of my classes, so I'm going to do these two with you kind of to finish out our notes. So if we didn't get to these, you'll have them. All right, so the product rule. I want to use the product rule to calculate the derivative of sine squared of x. Okay. Well, let's think about how to do this. So a product rule, when do we use a product rule? Yeah, it's when we have stuff with x's times stuff with x's in it. But I don't see stuff with x's in it times stuff with x's in it. So we're going to have to rewrite this a little bit to change it to be stuff with x's in it times stuff with x's in it. And sine squared of x, what that means is the sine of x times the sine of x. That's really what sine squared means. It's sine times itself. And so now I have something with x's in it times something with x's in it. And now that says product rule. So we aren't going to panic. We are going to go back to our product rule. We are going to trust our training, and we're going to say, when I do my product rule, I'm going to identify my first function as f. I'm going to identify my second function as g, and my derivative is going to be f prime times g plus f times g prime, and I'm going to plug everything in. Okay, so what we're looking for here, f prime. Well, that's going to be the derivative of the sine of x. The derivative of sine is cosine of x times g. My g as is, that's the sine of x. Plus f as is, that's just the sine of x as is, times the derivative of g, which is the derivative of sine. The derivative of the sine is cosine of x. And that's the product rule. So notice in the first one, these parentheses aren't really doing much. I've got a cosine times a sine plus a sine times a cosine. And really these are the same things because no matter which order I multiply in, they really mean the same thing. So this is really one of these plus another one of these. So I have two of those. You can write these in any order, whether it's sine or cosine. I'll just take the way I wrote the first one. And there we have the derivative of this. So this shows us how to do this with a product rule. Again, just rewrite it so that you have a product to apply the product rule to. And we'll see how to do this a different way on Tuesday. We'll rewrite it a different way to use something called the chain rule. We'll have some options on how to do that. We'll get the same answer either way, but for now, the product rule is what we have. All right, and then this last one, find the equation of the line tangent to this function at theta equals pi over 4. Okay, so we are finding the equation of the tangent line. Well, again, the equation of a tangent line is still the equation of a line. So to write the equation of any line, I need two pieces of information. I need a point and I need a slope. And we are not going to panic. We are going to just trust our training. We know how to do this. We did this before, and we're going to stick to our processes even when the numbers or the functions get weird or gross. So here we go. Our point, I know my x value is right here. It's pi over 4. I like x instead of theta, but you can really use either one. If you want theta there, that's fine. And then to find y, if we have an x, to find y, we're going to plug it in. So we're going to plug x equals pi over 4 into here to get y. It's going to be the tangent of pi over 4 times the secant of pi over 4. And we're going to have to go to our handy dandy unit circle. Pi over 4 is the one right in the middle. And the ordered pair there is root 2 over 2, root 2 over 2. And so tangent, this is y over x from our unit circle. Y root 2 over 2 over x root 2 over 2. Anything divided by itself is 1. So that's my tangent of pi over 4. Secant of pi over 4 is the cosine flipped upside down. Cosine is your x value. So I'm going to take root 2 over 2 and I'm going to flip it upside down. So my y value here is 1 times 2 over root 2, which is 2 over root 2. If you wanted to, you could simplify this. You don't have to rationalize, but in this case, rationalizing is going to simplify this a little bit. And so 2 over root 2, if I multiply that across, I'm going to get 2 times root 2. Root 2 times root 2 is just a 2. These guys will cancel, and I can just write that as root 2. So with your y values, you can either leave it as 2 over root 2, or we can use the simplified version of that, which is just root 2. This might be easier to work with and keep our numbers a little cleaner. But if you don't think of that, you can absolutely fight through it with 2 over root 2 as your y value. Okay, so that's my point. I've got an x value and a y value. That's my point. And then my slope, to get a slope at a function, that's my derivative, right? A slope is a derivative. So really, I have to find my derivative, dy dx, at x equals pi over 4. So I'm going to find my derivative, and then I'm going to plug pi over 4 into it. So we just have to do this. We're going to find our derivative. And then we'll plug pi over 4 in after we find it. So y looks like tangent of x times secant of x. Again, my brain likes x's better than thetas. We can do this with thetas as well. But my brain likes x's, so I'm just going to make these x's because my brain likes that better. And then to do our derivative, I have something with x's in it times something with x's in it. That says product rule, which means here's my f, here's my g, and we're going to rock with our derivative rule. F prime times g plus f times g prime. F prime, the derivative of tangent. You have to come back up to your handy dandy table. The derivative of tangent is secant squared. Okay, so that's my f prime, secant squared of x. G, my second function as is, which is just the secant of x, plus f, my first function as is, that's tangent of x, times g prime, the derivative of secant. If you need to head back up to your table, you can do that. This is going to be the secant of x times the tangent of x. So that's my derivative. I could simplify that if I wanted to. The secant cubed, right? Because 2 secants times another secant is secant cubed plus, I've got a couple of tangents, so tangent squared of x times secant of x. Okay, so this is my derivative. But again, to find my slope, I want the slope at x equals pi over 4. So I'm going to plug that in to my derivative. And that's going to be the slope of my line. So if I plug pi over 4 in, I'm going to get secant cubed of pi over 4 plus the tangent squared, of pi over 4. Let me plug that in. Pi over 4 times the secant of pi over 4. And we just found a bunch of these values. So the secant of pi over 4 was 2 over root 2. And again, I know that 2 over root 2 is also going to simplify to root 2. So I think I'm going to use this form because I think that's going to be easier to use. So I'm going to use root 2, and I'm going to have to cube that. Plus the tangent of pi over 4, we found that was 1. And I'm going to have to square that, times the secant of pi over 4, which again is 2 over root 2. But we found that that simplifies to root 2 if you rationalize that. So I'm going to use the prettier version of that. And let's see, root 2 times, or root 2 to the third power means root 2 times itself 3 times. And so what I'm going to have here is root 2 times root 2 is just 2. So I can write it like this. That's my slope. Oh, and I guess I can add those together. These are like terms. Sorry. 2 root 2's plus another root 2 gives me 3 root 2's. That's better. That's my slope. Okay, so now I have a point and I have a slope. Now we can either rock with y equals mx plus b, or we can do y minus y1 equals m times the quantity x minus x1. I think most of you use y equals mx plus b, so we'll start with that. You'll use your point for your x and your y, and we have our m right down here. So my y value is root 2 over 2, but again, I'm going to use root 2 for that. My slope, we simplified to 3 over root 2, or sorry, to 3 times root 2. That's my slope. My x coordinate is pi over 4, and then plus b. Now to solve for b, this isn't going to be pretty. You could put that in your calculator and get a decimal out, but for questions like this, Achieve is just going to say use symbolic notation. So you're going to leave it just like this. So to solve for b, I need to get b by itself. I need to move this over, so I need to subtract it from both sides. I know that's really ugly looking, but that just is what it is. So we're going to have root 2 minus 3 times root 2 times pi over 4, and that's my b value. So the equation of our tangent line, I have my m right here, I have my b right here, and sorry, I'm running out of space, so this is kind of a giant mess, but we're going to come back and do y equals mx plus b, leave y as y, we'll plug m in, which is 3 times the square root of 2, leave x as x, and then we'll plug our b value in, which is all of this. Don't panic, don't overthink it, just plug in this beautiful, horrifying number and put a box around it and put that in Achieve just like that. That will be the equation of your line. So again, even when things get hard and scary, I want you to stick to your processes that we know. If you're looking for the equation of any tangent line, you need a point and you need a slope. Use your OG to find your point, use your derivative to find your slope, and then rock with one of your line formulas. And fight through weirdo functions, fight through weirdo numbers, just follow your process. All right, so hopefully that helps you finish the notes and with a couple of things in your homework. I'm going to make another video to help you with the in-class worksheet that we didn't quite get to. So be on the lookout for that, and I will see you next time.